How are we doing today? Talk about chemical and physical properties and wrap up our unit with matter and energy. All right, so we'll talk about properties first. I'm going to go into some changes and do some quick review for the exam. All right, so physical properties, these are properties that are constants about the substance. These are things that you can observe using your senses. All right, in science, we use pretty much all of our senses in high school except for taste, even in college, but there are certain areas that you would use taste for some things in the real world, but we won't. So just the using your sight, touch, smell, and sound in some cases as well. All right, but these are things that you can observe without changing the substance or altering the substance. All right, we're going to go into what's called extensive versus intensive properties. All right, and all an extensive property is a property that depends on how much material you have, like volume. All right, this is something that would change based upon the size of the substance you had. So volume, mass, those things would change. Whether you had like a little drop of water or a whole pool of water. All right, so those are considered what we call extensive properties. All right, the other kind of physical property is called intensive. Intensive means it's something it's a property of the substance no matter how much you have. All right, like color or density. All right, those are what we call intensive properties. All right, melting points and boiling points are also intensive because it's dependent upon what the substance is, but not how much you have of that substance. Um, Physical changes we'll go over shortly, but these are changes that do not alter the substance. All right, these are things that can be reversed. Let's say you take a piece of paper and you crumble it up, or you make Kool-Aid. All right, a lot of people think making Kool-Aid is a chemical change. All right, making Kool-Aid is a physical change. You can actually get the Kool-Aid and the sugar back, um, either by a slow process called evaporation of the water, or a quicker process of distillation of the water. But physical changes can be reversed. Changing phase is also a physical change that people don't realize. You melt an ice cube. All right, you can turn that liquid water back into solid ice by just lowering its temperature. All right, so we move on to chemical properties. Chemical properties are properties that we can only determine by reacting the substance first. All right, so it's how it reacts with other substances. All right, so chemical changes, some examples of chemical changes. You can see pictures over to the side. All right, classic things. If you were in 8th grade science, you can identify a chemical change if it changes color, changes temperature, that's heat. If it gives off bubbles, um, things like that. I'm trying to get the pointer. All right. So over here we have a fire, which is an obvious chemical property or chemical change. Down here is supposed to show rusting on a nail, on an iron nail. Those are all classic examples of something that is changing properties or changing what the actual substance is. A chemical ice pack. All right, these things right here, the ones that you take out, they have a liquid in them. You pop the liquid, it reacts with the solid that's in the baggie, and those will be cold for a short period of time. All right, once the reactants run out, they stop working. All right, some quick examples or quick comparison of chemical and physical changes here. All right, so chemical change is performs or forms new products. It changes the substance. Chemical change or physical change just changes what it looks like, so to speak. All right, so you got examples up here of combustion, which is fire, rotting of a pear, rusting. Digestion in your stomach is chemical digestion. Digestion in your mouth is primarily mechanical, although your saliva does do some chemical digestion. It's primarily mechanical up in your mouth, but in your stomach, there's definitely chemical digestion going on. Physical changes, like I said, melting, shredding or tearing paper, boiling, which is a changing phase. All right, chopping or breaking it up or ripping up substances is also a physical change. So here we go, some physical changes that you may or may not be aware of. You take peanuts and you grind them up and you're going to make peanut butter. All right, so that's a physical change. Now, could you really get the peanuts back again? Probably not. All right, but what happens is you don't change the identity of what the substance is by grinding it. You got some paper. All right, if you want to get fancy and do some origami, you can make a paper airplane or other objects. All right, so that's just folding. You don't change what the paper actually is, you just change what it looks like. I said before, Kool-Aid. All right, you take Kool-Aid, you dissolve it into water, and you can make Kool-Aid. All right, you could get those two things separated again, process of distillation, which is separate substances based upon boiling points, or just slow process of evaporation. Here we got a glass of ice. If you leave it out in room, it will melt and it'll turn into liquid water. Both are still the same substance, so you got the ice and the water are the same substance, all right, but they are just in different phases. And you can go back and forth all the time between solid water and liquid water, and you can do that with all substances as long as you can get to the correct temperature for that to happen. Some examples of chemical changes would be taking an egg and cooking it, all right, or frying an egg, right? So it definitely takes on a different appearance. You can never get Once you have this egg, you're not going back to what this egg was. You've actually changed what the protein structure is in that substance. That's a bowl of cake mix. You bake it, and you get a cake. All right, so you actually change the properties of the substance to make the cake in this case. That's a piece of newspaper. All right, you can burn the newspaper, you're left with these charred remains. All right, but it's definitely a different substance. Doesn't have the same mass as it had before. You think of wood. If you have a wood fireplace, if you have an actual wood burning fireplace in your house or a fire pit outside, think about all the wood that you put in and the mass of it. All right, and the ashes that are left afterwards have nowhere near the mass of the wood that you put in. That's because a lot of the mass of the material went up in the smoke as carbon dioxide or carbon monoxide or other byproduct gases. All right, we have a car down here. All right, it rusts. All right, and turns into some, car there. All right, it's definitely not the same material. If you guys have ever touched rust, it's not nearly as strong as the metal that it came from. It's just some videos. All right, so here we go. So we're gonna do a couple practice ones. I will test you on, quote unquote, question you on the last couple. But we'll do the first one or two together. All right, so what I want you to be able to tell me is, are these things an intensive property, an extensive property, or a chemical property? Obviously, intensive and extensive are both physical properties. All right, so we want you to get specific if it's a physical property, and then just tell me if it's chemical property. All right, so the mass of a copper wire is 325 grams. That is something that you do not need to react it with something else to figure out. You can just put it on a scale. So that's definitely a physical property. Now, is it intensive or extensive? That depends on, your understanding of those. All right, this is an extensive property because it is a property that depends on what the mass is or how much you have of it. All right, so that one, the mass of anything would be an extensive property. All right, the boiling point of ethanol is 77 degrees Celsius. All right, boiling points and melting points, or condensation points or freezing points, they're all the same or similar. Those are all properties or temperatures we can measure without altering what the substance is. You just heat it up or cool it down to change the phase. All right, so therefore they're not a chemical property, they're a physical property. All right, in boiling point, if you have the boiling point of ethanol, it doesn't matter if you have 3 ounces of ethanol, 3 gallons of ethanol. All right, it just matters that it's made of ethanol, so it's gonna have the same boiling point. Therefore, it's an intensive property. Okay, baking soda reacts with vinegar to make CO2. You guys know this if you ever baked a cake. That's where you get the little bubbles or the air pockets in there to make the cake rise a little bit. All right. So baking soda. So this is something that actually alters the substance of what it is. All right. You make the CO2, which was not present before, but it came from the elements that are in the baking soda. All right. And reacted with the heat and other things in there. All right. So this is an actual chemical property. Okay, so we kind of gone through an example of each of these. Now, the last two you're going to have to figure out on Edpuzzle. So here we go. All right, so the density of mercury is 13.6 grams. Pause for a second. All right, density is not a chemical property. You don't need to alter the substance to figure it out. So therefore, you got to figure out if it's intensive or extensive. All right, does density depend on how much you have of the substance? It does not. So since it does not depend on how much you have, then it's said to be an intensive property. All right, I believe this is the last one. The solubility of sodium chloride in water is 40 grams per 100 mils of water. All right, solubility is not a chemical property, so it's definitely physical. So now, does how much dissolved depend upon how much you have? And that's absolutely correct. It does depend. So it is an extensive property. Okay, so that's just a quick, hopefully it's a review. This is something you might not have done intensive or extensive in younger grades, but you definitely talked about chemical and physical properties in younger grades. All right, so here we go. Since we have the test coming up, we'll do a couple, we're going to kind of challenge you with some 3 problems to see if you can figure these out. They're up on the screen here combined, so you can pause them and write them down. I would recommend doing that and just kind of do them all at once and then go through the video to see what the answers are. All right, so the first one says, calculate the final temperature of 475 joules are added to 15 grams of water at 15 degrees Celsius. All right, so here we go. Phase change or temperature change. Since it's talking about a final temperature, it's asking for a final temperature, it's got to be a temperature change formula. Since it's a temperature change formula, it's going to be the Q equals MC delta T formula. Remember, Q is in units of joules, M is mass, which needs to be grams in this case. C stands for specific heat, all right, which if it's water, which this says it's water, you can find the specific heat on your reference tables, 4.18 joules per gram degree Celsius for liquid water, and then delta T just means a change in temperature, okay? So you just basically plug and play. We're solving for delta T in this case, but that's going to be step 1 of the process. Then we got to do a step 2 to get the final temperature. All right, so the Q is 475 joules. The mass they give us is 15 grams. Since it's water, its specific heat is 4.18 joules per gram times degree Celsius. All right, and then I told you we're going to solve for delta T in this case. So to do this, you're going to have to multiply 15 times 4, all right, which is going to be somewhere around 60. That's just a ballpark number. And then it's 60 delta T. To get delta T by itself, you have to divide both sides by 60. So your final answer is going to be 475 divided by that 60 number, whatever it is here. I'm just canceling out units. And you get 62.7 joules per degree Celsius for the times delta T. To get delta T by itself, you divide by the 62.7, canceling out units, and you get 7.58 degrees Celsius. Now that's the temperature change, not the final temperature. So to figure out the final temperature, you can do it logically, or you can just use the delta T formula. I recommend use the delta T formula, that you never really get screwed up. Delta T is T final, which is final temperature, minus Ti, which is initial temperature. Since our delta T we solved to be 7.58, that's going to go in for our delta T. Right? We don't know our TF, that's what we're finding, so it just gets dropped down. And then our initial temperature we get from the problem up here at 15 degrees Celsius. So our initial temperature is the 15. Now we have to get TF by itself. Since this is a minus sign right here, we have to add 15 to both sides. All right, so it's 7.58 plus 15. All right, and when you solve that, you get 22.58 degrees Celsius. So hopefully that's a review. That's review. With the test, you're going to have to do these in a fairly quick fashion because you're going to have multiple questions on the test. So, a problem like this, I would probably budget for you guys maybe 3 minutes, maybe 4 minutes. All right, so you don't have a lot of time to go through it, but you do have to be able to answer it fairly quickly, which means you got to get started quickly on the problem. All right, next problem. What's the total number of kilojoules of heat needed to vaporize 169 grams of water at 100 degrees Celsius? All right, first question you ask yourself, is it a phase change or a temperature change? All right, so it says vaporize. So hopefully you recognize that that's a phase change. All right, so that's going to be Q equals mH to V since it is vaporization. All right, so they give us 169 grams of water, so we put 169 in for mass, and then the heat of vaporization of water is on your reference tables, which is 2260 joules per gram. All right, you solve for Q, and you cross out units here. Sorry, I forgot about that step. And then you multiply these out, and you get 381,940 joules. Be careful. This question asks for kilojoules, but we have joules, so you have to be able to go between the two. All right. I always remind you of King Henry died by drinking chocolate milk. All right. So here's our kind of conversion chart. King Henry died by drinking chocolate milk. Kilo, hecto, deca, base unit, deci, centi, milli. So where do joules go on here? Joules go under the base. Kilojoules are over here. So we have to go, so we're starting at the base and we have to go to the K spot. So we have to go 1, 2, 3 places to the left. So our decimal point is here at the end of the number. So we have to go 1, 2, 3 places to the left. So we get 381.940 kilojoules, or I rounded to 382 kilojoules. All right. So, the catch in this problem, so to speak, was recognizing that it did not ask for joules, it asked for kilojoules. So just pay attention to those details when you're doing these problems. I'm not going to try to trick you on the test, but these aren't really tricks. These are just normal problems. All right, last one. When 35 grams of a substance are completely melted at its melting point, 4,550 joules are absorbed. What's the heat of fusion of the substance? So phase change or temperature change. Since it's specifically asking for heat of fusion, it's Q equals mH sub F. You give us 35 grams, right? They give us the 4,550 joules, and they're asking for the H sub F. So don't plug in the H sub F for water here because it doesn't say that it is water. All right. And a lot of times I'm seeing people put in a number for Q, for M, and H, and then you have no X value. You don't have nothing to solve for. All right, so here the Q is 4550. The mass is 35 grams. H of F stays as H sub F. Solve for H sub F, you just divide both sides by 35, and you get 130 joules per gram. Okay, that's it here. I recommend you guys doing problems in your review books for the exam to practice. Okay, have a great day.